If this is your first time joining, we hope you find this webinar informative and insightful. We look forward to having you join our future sessions as well. Before we get started, a couple housekeeping items. So you're going to be in a listen-only mode, so your lines are automatically muted. But if you want to submit a question, go ahead and locate that questions pane in the control panel there, and you can send in those questions at any time during the presentation. Our subject matter experts on the line here, myself and Nick Turner, are going to be on to answer those questions throughout the presentation. Today's presentation is going to be presented by Stephen Cooper, one of our technical sales engineers here at Ekahau, and the topic is going to be real-world Wi-Fi data rate versus throughput. Stephen, you on the line?
Yeah, thanks very much, Jerry, and thanks to you both for joining us in completely wacky hours in your time zone, for joining us for this APAC webinar. So thanks very much everyone for joining. This is the third webinar that we've done for the Asia Pacific time zone, so thank you for coming back. As Jerry mentioned, we're going to discuss the differences between some of the Wi-Fi marketing hype that you might have seen out there in the vendor world, and have a bit of a discussion about data rates and what sort of throughputs are more realistic and why we end up with those real world throughputs. So if you followed the previous webinars we did, the last one was talking a bit more about how 802.11 as a protocol operates, and that's sort of going to be covered a little bit in this presentation as well, and how that impacts real world throughput. So the agenda today is we're going to briefly cover that 802.11 standard and talk about the Wi-Fi Alliance and the IEEE and what they have to do with how things are marketed and you know, the 802.11ac, N, A, B, G, all of those logos that you see around on devices these days. We'll talk a little bit about the vendors and the marketing side of the equation, so you have a bit of insight as to obviously what they're trying to achieve and why it is that they pitch things that way. We'll talk about the environments of wireless and what impact that can have on data rates. We'll speak about what impact legacy devices can have on data rates and throughput. We'll talk about doing design using Ekahau Site Survey and what you can aim for, what metrics you can aim to optimize to get the best real-world throughput. We'll briefly cover a little bit about airtime utilization and throughput in a couple of slides, but I'll also go into a little bit more detail later on. I'll do a little quick demo in Ekahau Site Survey of a couple of the visualizations that we have, so you can better understand those. And then we'll talk about the next steps, as you know, what you can do with Ekahau Site Survey, how you can learn more, where you can get some more information, and where to go from there. And we'll wrap it up. Like I said, we'll do a little bit of a demo in Ekahau Site Survey and show you what that actually means when you're using the software. And then we'll wrap it up with a Q&A session, which Nick and Jerry will help out. So as I mentioned, feel free to ask any questions via the Q&A box as we go, and they'll do their best to respond to those questions as we go throughout the webinar. No questions are stupid questions, so feel free to ask anything as we go along, and we'll try and tackle them all at the end. All right, so most of you have probably heard about the IEEE, and it's the Institute of Electrical and, I've actually forgotten what it is. Institute of Electronics and, Nick, Jerry, do you remember what it is? Anyway, not important. We'll keep talking about the IEEE. So basically, they set the standards for a lot of our communications protocols, not only just 802.11 Wi-Fi, but even Bluetooth, 802.15, a lot of other standards that we see out there in the environment. So they will have a range of different categories within the IEEE that focus on different engineering standards. So not just communications and spectrum, but they deal with anything to do with electronic engineering and electrical engineering. And they work with the community using publications and feedback and conferences to develop these standards. And in terms of Wi-Fi, they actually basically they helped form the 802.11 standard back in 1997, and since then all of the amendments and improvements and updates that have happened to that standard have been done through 802.11 working groups through the IEEE. So the Wi-Fi Alliance, they work closely with the IEEE, but basically the Wi-Fi Alliance is an independent global organization that promotes the growth of Wi-Fi technology. So aside from the IEEE working on the standards side of things, the Wi-Fi Alliance focuses on the devices and what users use the technology for. And they basically set the guidelines for interoperability across vendors. So back when Wi-Fi first started, early in the early days in the late 90s, you typically have proprietary implementations of communications protocols based loosely on what the 802.11 standard was, but you would have vendors put out these Wi-Fi APs, and they'll put out Wi-Fi chipsets. So as you can imagine, laptops and desktops back then didn't have built-in Wi-Fi adapters. So they would sell you their brand access point with, a dozen wireless adapters that they would give you. And it was only those adapters that could work with those access points and vice versa with their proprietary communications protocol. You couldn't use those adapters to work with any other vendor's access point because they implemented 802.11 slightly differently. So Wi-Fi Alliance stopped all that from happening and basically focused on interoperability. And so today, when you see an 802.11 Wi-Fi router, whether it's a home router or whether it's a 802.11 access point used in the enterprise, you'll see these Wi-Fi logos on there and telling you what standards they're capable of doing, just like your laptops and phones and other devices will show you the same sort of specs. So it's basically giving you a guarantee as a user that it can operate on that level of standard. So vendor marketing, I'm sure we've seen this not only in Wi-Fi and IT and communications, but you see it everywhere. Everyone's trying to pitch their products as the best. So you get some vendors which are quite open and honest about the statistics and capabilities of their devices, and you'll see some other vendors which just completely exaggerate things. So the 802.11 standard in a lot of areas, it tells you what the theoretical maximums are, and there's a lot of capabilities built into standards. And they don't always see the true light of day, those capabilities. For an example, 802.11n was supposed to be able to do up to 4 spatial streams, but we never saw 4 spatial stream capable client devices for 802.11n. And we're seeing the same thing now with 802.11ac Wave 1 and now with Wave 2. 802.11ac Wave 2 devices and access points can actually have up to 8 spatial streams. That's defined in the standard, and the specifications around that are defined in the standard, and the speeds and throughputs that you can get from that theoretically are defined in the standard. But there's just none of those devices on the market. You don't even really see, you see 4 spatial stream access points, but you don't see any 4 spatial stream capable clients. This MacBook Pro that I'm presenting on is one of the most capable Wi-Fi devices that we typically see. It can do 3x3x3 spatial streams, whereas your smartphone might do 1 or 2 spatial streams. A tablet might do 2 spatial streams. So every device is different, but that's where it starts to bleed into what the real world usability is, or what's even available in the real world is not what the standard says is necessarily possible. So when you see a lot of the data sheets from vendors, when they're saying their maximum speeds and things like that, and we talked in the last webinar about vendor defaults. So it's often said in the wireless industry that a vendor default is not necessarily a vendor recommendation. On the same side of that, vendor marketing speak is basically just to sometimes compare themselves to the competitors to try and make themselves seem better, so that when you're doing a side-by-side speed test, when you get the AP out of the box, it's going to perform to the best of its abilities with the default config. But that advertising on the box is often misleading, and it's usually the theoretical maximums that you could get with an 802.11ac Wave 2 access point with 4 spatial streams with the highest signal to noise ratio with 160 megahertz wide channels, and it's just not feasible in today's wireless environments. We covered co-channel interference in the last webinar and the impacts of having 20 versus 40 versus 80 versus 160 megahertz wide channels. So feel free to revisit that webinar on our YouTube if you want some more information about the impacts of wide channels. But we basically talked about how it's impractical to have that in today's environments, even if you're trying to get those sorts of speeds out of your network. So the wireless environment is made up of not only Wi-Fi, but there's also non-Wi-Fi traffic and noise in the environment. So access points, they're trying to get their signals around walls and water effects and non-Wi-Fi interference, such as cameras and drones and motion detectors. So all of this impacts on your signal. And one of the big metrics that's quite important for Wi-Fi networks to operate well is signal-to-noise ratio. So we'll talk a little bit more about that in the next slide. But basically, the key point I want you to remember to take away from this webinar is that data rates are highly influenced by signal-to-noise ratio. So if we do a quick look at the theory behind data rates, and if we look at general RF theory around channel capacities, so if we look at channel capacity and bandwidth, and you can consider bandwidth in the terms of Wi-Fi as, whether you're using 20, 40, 80 or 160 megahertz wide channels, that's where you can use this math calculation to sort of work towards what is potentially achievable as a theoretical maximum for throughput on that particular bandwidth that you're using. But you can see there on the right-hand side, signal over noise. That's what I was saying. Signal-to-noise ratio is one of the big factors in determining what sort of data rates you get. So in terms of 802.11n and AC, and we're going to be moving into 802.11ax in the near future as well, it's not just the channel bandwidth that introduces better capabilities and speeds, but also spatial streams, which is determined in terms of the capabilities of the chipset to receive multiple streams at the same time. And that's where I was alluding to different devices such as MacBook Pros can do 3x3x3. Phones, sometimes they can only do one spatial stream or two spatial streams just because those components are often designed to be cheap to save money, or maybe even the vendor chooses a one spatial stream device to sort of save on battery power for a smartphone. Down the bottom right-hand corner, we have 4x4x4 spatial streams, and I think we've only ever seen those sorts of devices in a test lab environment where a vendor would be testing the full capabilities of that. There's definitely no retail consumer-grade 4x4x4 spatial stream devices that we know of in the world today. And there probably won't be, to be honest. Everyone's starting to focus on 802.11ax, so that'll be the next focus for all of the Wi-Fi chipset vendors. So again, I just want to highlight signal-to-noise ratio is the big influencing factor on data rates. So talking about interference on a couple of slides back, there's a lot of things that can actually influence a client's decision as to what data rates it will operate at. And there's actually a part of the 802.11 standard defines the parameters of dynamic rate shifting, which can be influenced by a few different things. The easiest one to picture in your mind is distance from a access point. So distance between the sender and the receiver is the biggest influence on data rates. So the further you move away from an access point, not only do you lose RF signal, but your data rate will start to decrease to sort of maintain that quality of connection. And again, that's a big influence on signal-to-noise ratio. As you get further away from an access point, your signal is going to decrease, and hence your signal-to-noise ratio is going to decrease. The background non-Wi-Fi noise, that impacts your noise floor. So that's the noise part of the signal-to-noise ratio equation. So if you have excessive RF interference, whether it's a microwave or a wideband jammer, that's going to raise your noise floor. And you might have a really good signal close to the access point, but if your noise floor gets high enough to a certain level and your signal-to-noise ratio starts dropping, that's going to impact your data rates too. So even Wi-Fi interference, such as co-channel and adjacent channel interference that we discussed on the previous webinar, that will impact data rates as well, and impacts the available real-world throughput available on a channel, because as soon as you have overlapping channels, you're effectively reducing your throughput available on that channel due to Wi-Fi being a shared medium and each radio or wireless device is contending for access to that channel. Transmit power, again, that also comes back to the signal part of the equation of signal-to-noise ratio. So you could have an imbalance in transmit power between your access point and your wireless device. If your wireless device can't transmit back and get any acknowledgements from the access point, it might try and retransmit at a lower data rate to try and make sure that that transmission gets through to the AP. Capabilities, again, we've discussed spatial streams. So this also affects the rate that the clients can associate to. So dynamic rate shifting basically adjusts the data rate to promote more efficient communications and reduce the retransmissions that are seen in the network. So this is just a little diagram taken from an Aruba document. This is based on 802.11 A, B, and G, just using up to 54 megabits per second. But you can sort of see as you move away from an access point, and whether it's your 5 gigahertz or 2.4 gigahertz signal decreases, you've got there in the blue text the signal to noise ratio decreasing. You can see how that impacts the data rates in this little figure there. So this is a very a brilliant slide here that I've got. There's quite some experts in the community. Keith Parsons at Wireless LAN Pros has helped put this together using data from various calculators and things. Andrew Von Nage of Revolution Wi-Fi also had some excellent calculators for MCS rates and signal to noise ratio. There is also one of these for 802.11n, but AC is what we're using mostly in these days. So MCS Index stands for Modulation and Coding Scheme. And this is basically giving you an idea of the modulation scheme and the coding mechanism that's used, and the sort of efficiency that you should get out of that coding scheme. And the more complex the coding and the higher the modulation scheme is. So 256 QAM, you can go up to 1024 QAM with 802.11 AC Wave 2, but it's definitely going to be available in AX. The higher and more complex that modulation is, the better quality signal you need to have. So let me just do some annotations on here. So we have the signal to noise ratio column here in the 20 megahertz table, which is probably the most important one to focus on there. And one of the features of high throughput or 802.11n and VHT 802.11ac is the ability to have a short guard interval, which is what this 400 nanoseconds represents in this table here. So a typical network would have the long guard interval from legacy networks, or even if you have a legacy client on your channel, you might fall back to the long guard interval. But typically, most networks these days, your devices can take advantage of a short guard interval. So when you look at MCS rates on the left here, and you combine spatial streams, which is to do with the capabilities of your access points and devices, you can start to get an idea of what sort of association rate you would get. I know in my experience, I've had a lot of customers and even colleagues that have asked, you know, why am I only getting associated at this rate? Or I'm doing a speed test and I only get this throughput. You know, they might have a 1 gigabit per second internet connection, but wondering why they're only getting 100 megabits per second throughput. Or you might even get some users which are using MacBooks and they're a bit more clued up, and they know how to get to the hidden menu of pushing option and clicking on your Wi-Fi signal, and that tells you some cool information such as your signal strength and your SNR and your MCS index and what your data rate is. So that is also directly correlated to this information in this table, where you can do a bit of looking up and some guesswork and going, oh, okay, I've got a 2 spatial stream capable device, and this is what my SNR is at the moment. You know, let's say I'm doing an SNR of 20, and I've got 2 spatial streams. I should better get one of these sort of association rates here. Really, the big factor is whether I'm using a short guard interval or a long guard interval. And one of the other big factors in terms of quality of the connection is measured. Well, it's not measured, but it's a factor of multipath. So if you're in an environment with lots of walls and reflections around, or a lot of obstacles in between your AP and yourself, you're probably experiencing multipath in that environment. So to further to make that connection further robust, your Wi-Fi radios will then fall back to having a long guard interval to sort of protect from the effects of that that multipath there. So that's where you might get this lower rate on this side. So I'm not going to go into too much more detail about that. We'll sort of come back to that in the demo later on, but definitely have a look at that URL there. Go to the Wireless LAN Pros site and download this chart. I can guarantee it'll be quite useful for you, especially when you're having conversations with the users about why rates might not be what they're seeing. So briefly spoke about legacy devices before. So we got a nice little analogy of a slow old car there versus a supercar here. So legacy devices are a big impact on your network in terms of the data rates that you have. So You probably know that 802.11 802.11b and G and N, they're all sort of backwards compatible with each other. 802.11n on 5 gigahertz and A and AC are all backwards compatible with each other. There's actually some protection mechanisms that are defined in the 802.11 standards that basically says, okay, yes, you can be backwards compatible and have this mix of different devices on your network, but as soon as you have a legacy device on your network, it completely changes the way that every other radio on that channel has to operate and fall back to those data rates to basically be backwards compatible with those older legacy devices. So you often see a lot of best practice recommendations where, for a wireless design, it's recommending to disable legacy 802.11b data rates. So, 1, 2, 5.5, and 11 megabits per second. If you set your wireless access point minimum basic rate to above 11 megabits per second, so maybe 12 megabits per second, you've immediately cut off the capability for any 802.11b devices to associate and work on your network. So there's a lot of caution that is put around that. So obviously, if you were running an environment, maybe you've got 5 gigahertz and 2.4 gigahertz, perhaps you're in the situation where you need to convince your IT team and your users to move your corporate traffic to 5 gigahertz because there's less congestion, there's more available channels and bandwidth to use, but maybe 2.4 gigahertz is used for best effort traffic or maybe legacy devices. So if you still had to support maybe old barcode scanners that had to work on those lower rates, then you'd probably try and move to a band steering scenario where you've got all your important traffic and devices on 5 gigahertz and all the old nasty stuff that's slow, just restrict that to 2.4 gigahertz. And chances are those old devices probably are only capable of 2.4 gigahertz. Another interesting scenario is you might have devices that are capable of higher data rates, whether it be on 2.4 or 5 gigahertz bands, and you might have the best intention of improving your operation of your network by trying to reduce your cell edges by increasing those minimum basic rates, but you might actually inadvertently cut off some of those devices too, because there are still some devices where the chipsets require that they can associate at lower data rates, such as 6 megabits per second or something like that. So there is a lot of caution to be had around that, and definitely pay a lot of attention to what your device capabilities are in terms of data rates, but also keep in mind that just having one slow old legacy device on your network can slow everything else down and is a big influencing factor on data rates. So this is where we go and talk about design, where you can use a tool such as Ekahau Site Survey to input all these different capabilities of devices. You can put in different spatial streams. You can put in whether they're capable of 20 versus 40 versus 80 megahertz wide channels. And you can basically visualize with Ekahau Site Survey what impact it's going to have. And you can also specify things such as whether radios are capable of using the short guard interval, and things like that. So let's just have a quick look here. Airtime utilization is one of the heat maps that we use, which is a predictive measure to determine how much airtime is going to be utilized based on the number of devices we have, the sort of traffic or throughput that we're expecting them to have over these wireless radios, and any overhead from SSIDs and things like that. So it's quite a useful utilization visualization to look at. Throughput versus data rate. I'm going to go a little bit more into that detail in the demo because we do have both visualizations. Often people can be confused between the two. So I'll cover that a bit later. But basically we have data rates, which is a predictive visualization based on the capabilities of the access points that you're placing in your predictive design. The data rate illustrated by that heat map is theoretical maximums based on your configuration that you have specified. So channel width, access point model, because we know in Ekahau Site Survey, when we put in the access points, we know their antenna radiation patterns as well as their specs and capabilities. So we know that an Aruba access point can do such and such spatial streams as well as this channel width. So that goes into the calculation of the data rate from a predictive design point of view. You can use throughput from a predictive design point of view, but it's basically using a guess of what some of the Wi-Fi interference or noise is impacting on the signal to noise ratio and reducing that data rate down to a more real world throughput. But again, it's just a predicted calculation. the most useful use of that throughput visualization is when you've done a post survey or a live operational survey and you've done an active throughput survey using an iPerf server. That's when you get real world throughput results from that iPerf test. So I'll give a quick overview of the Ekahau solution for those of you that don't know before we jump into a little bit of a demo. So we've got 3-day Wi-Fi planning. We have the capability to automatically detect walls from CAD files, capacity planning and analysis, as I mentioned before. Capacity planning is a big part of the equation these days. It's not good enough just to plan for coverage everywhere. Sure, you have to meet your primary and secondary coverage requirements, signal to noise ratio, number of AP visibility, all of that. Good stuff, but you do have to plan for capacity these days. And that's just not number of devices, but it's also where they are in your network and what sort of traffic they're going to be using, whether it's video streaming or Skype or web and email traffic, or maybe they're just barcodes with a little bit of blips here and there. And it helps you basically get an idea of how congested your network might be from the get-go. Site surveys, I touched on it briefly. We've got passive surveys, so that's measuring all of the Wi-Fi and spectrum on the Ekahau Sidekick there. Active surveys is when you actively associate your Wi-Fi NIC in your laptop or tablet to a network, and you can perform a ping active survey, which gives you measurements of round-trip time or packet loss, versus a iPerf throughput survey, which is what I mentioned before, to give you some real-world throughput data. And we've also got spectrum surveys, which is what the Sidekick is doing with its dual-band spectrum analyzer. And we have fully customizable reporting. So with all these capabilities that we have to do a predictive design as well as a survey, you can present to your customers or even your colleagues or partners that you've designed for these types of devices in this sort of environment based on these coverage and capacity requirements. And it also helps you to illustrate what the real world throughput should be. So you can do the predictive data rate side of things and say, well, this is the marketing speak, but then here's our real world throughput survey of what we've actually done, and this is what we expect. And so what we've been speaking about in this webinar should hopefully help you bridge that gap between, well, why is the data rate throughputs, the data rate visualization so good versus the iPerf throughput survey that we've done is not quite meeting that up. So that's where you have that conversation and educate your customers and users around what data rate actually means in the real world. So it wouldn't be an Ekahau webinar if we didn't talk about the Sidekick. So those of you probably already familiar with the Sidekick, we came out with it last year in October. It's an all-in-one survey device, first of its kind in the market, where it's got dual 802.11ac Wi-Fi radios in it, sort of what you'd find in your enterprise-grade access points. And it's got a built-in 8-hour battery, which enables you to survey for the whole day without draining your laptop and tablet battery. And basically having the dual-band Wi-Fi radios as well as a dual-band spectrum analyzer, which is near real-time in terms of its visualization and resolution, basically gives you that quicker and more efficient troubleshooting. So I'll show you, even though this is not a Wi-Fi troubleshooting webinar as such, I'll give you a quick snippet of what the Sidekick can do at the end of this webinar. So Ekahau partners with all of the major wireless LAN vendors: Cisco, Meraki, Aruba, Ruckus, Fortinet, Maru, Aerohive. All of their SEs love our tools. They use our tools. Even the Aruba and Cisco training requires you to know how to use Ekahau Site Survey, which is pretty awesome. So it's very complementary. When you look through our library of access points, you see all the usual vendors and models in there. So we have not only indoor access points, but also outdoor access points. We have indoor access points with omnidirectional antennas as well as external antennas, and the same for outdoor. So you can do office deployments, you can do planning for warehouse deployments, you can do planning for outdoor university campuses. So it suits all of the scenarios that you're working for. So the next steps are you can schedule a demo with myself or even Nick, who's on the call. Maybe not with Joel right at the moment because he's enjoying a nice holiday overseas. How dare he? But you can get in touch with us on Twitter. Those are our Twitter handles there. Or you can go on the website and request a demo or an evaluation version to get yourselves familiar with Ekahau Site Survey. We also recently came out with a collaborative book. Joel and Jerry both contributed to the content of that on Wi-Fi network design for dummies. And that actually covers some of the topics that we've spoken about in this webinar, as well as the previous webinar on co-channel and adjacent channel interference. And it helps you better understand what are the key elements of designing a good Wi-Fi network are, and what can impact the operation or throughput or performance of your network. So yeah, I definitely recommend going ahead and downloading the ebook from that link there. A lot of people ask about our training courses. They might have been using Ekahau Site Survey for a while, but they ask, what's next? How do we become an expert in this? So the great thing is we have a 4-day certification program, Ekahau Certified Survey Engineer, trained by some of the industry experts that you can see there on the right-hand side. And the great thing is that sort of the first 1.5 days is all about Wi-Fi and RF fundamentals. It talks everything about how the protocol operates, how devices operate, how they make decisions to roam and connect to the network. And you cover all of that even before you even touch Ekahau Site Survey, but you're prepared with that knowledge up front of how to best design a network before you even start to design a network. And then you cover things such as surveying and troubleshooting and reporting. So I highly recommend that. I've just popped up a few dates there on the screen. Given that this is an Asia Pacific webinar, we've got some exciting dates there coming up for some courses. So feel free to reach out to me if you want some more information on those courses. I'll leave our details up there on the screen just for a little bit. So if you need to write down our email addresses or Twitter handles before I jump into a demo, I'll also come back to the screen as we do some Q&A. So what I will do is I'll just end that now and switch over to Ekahau Site Survey. So you should all be able to see that on my screen there. So just for a quick demo point of view, I've got a sample floor plan here and a project plan with a requirements area, and I've got an access point placed there. So I've got an Aruba 315 access point, and I'm currently on the data rate visualization for 5 gigahertz. And you can see down the bottom here, we've got 3.5 gigabits per second is the maximum data rate. So I just wanted to show you what can influence that and how you can play around with that in Ekahau Site Survey. If we go over to the left, let me just highlight this over here on the left-hand side, you can actually go into the details of that access point configuration if you just select the AC radio. And you can see in here we've got a number of supported spatial streams. So that's actually taken from an Aruba data sheet when we fed that in. I'm actually going to show you a data sheet of this AP in a second. And we're also assuming that we can use the short guard interval. So that's where I was mentioning before. If we had a legacy client on our channel, it's not so much going to be the case on 802.11ac, but certainly for 802.11n, if you had a legacy B or G client on there, you probably won't be able to use the short guard interval. You'd be back to the long guard interval. Or if you're on a 5 gigahertz 802.11n or AC network and you've got a lot of multipath between yourself and your access point, you're possibly going to fall back to using the long guard interval. So if we untick this, you'll see that the maximum data rates drop back to 3.2 gigabits per second because there's additional protection mechanisms in there to make the encoding and modulation more robust, just because we've changed from short guard to long guard interval. Even if I change the spatial streams to 3 spatial streams, that's had a big impact on what this real world throughput maximum could be, 2.4 gigabits per second. So let me set that back to the 4 spatial streams. So you'll see at the moment, we've got a channel 36 at 160 megahertz wide channel. Let's just go ahead and redo its channel plan based on 80 megahertz wide channels. And you'll see that's dropped almost half there because we've got half the available bandwidth. We've got half the theoretical maximum that we can actually use there. I certainly don't recommend deploying 160 megahertz wide channels, and definitely do 80 megahertz channels with cautions, but this is where we start to go into, okay, we've seen on the box what this device can do, or on the data sheet, we've got our users saying, hey, why can't we do this? Or maybe they've been sneaky and used the option button on their Mac and can see that you're only using 20 megahertz wide channels. But if we're using 20 megahertz wide channels with 802.11ac, 360 megabits per second is the theoretical maximum we could get using the short guard interval with no other co-channel interference, with no other legacy devices, with perfect signal to noise ratio, everything else all lined up and magical. That's what our association rate would be. Doesn't mean that's what the real world throughput is, because 802.11 is a half duplex protocol. So there's other factors in terms of overheads and the way that 802.11 works as a protocol, how it communicates, how it checks for whether the channel is clear or not. Your real world throughput on this particular one radio here, if your device had 4 spatial stream capability, would be probably half that. So maybe 180, maybe 200 megabits per second if you're lucky. Now remember, I mentioned earlier that we haven't seen any 4 spatial stream devices on the market. So if you did this as 3 spatial streams, we could basically simulate that by changing this radio back to 3 spatial streams. Say if it was my MacBook that I had here, it's then dropped it down to 300 megabits per second. So I might be lucky to get 150 to 160 megabits per second between my MacBook and the access point. Obviously, if you've got a slow WAN link or internet link that's slower than that, you're not going to get that real world throughput end to end. But between the wireless device and the laptop, that's where it can make a difference. So just wanted to highlight that a little bit before going into a Q&A. Let me just bring our contact details back up again before we do that. All right, Nick and Jerry, did you have anything to add before we get into a Q&A session?
Oh, very good stuff, Stephen. Yeah, we've got a couple of questions that have come in here that I think will tee up nicely to talking about the sidekick that you already kind of alluded to a little bit in the presentation. But yeah, I think you covered all the all the important stuff there. There's nothing else that I would add off the top of my head.
Great.
Yeah, same thing here. I guess the one question would be like, do you have a good answer for why do these vendors offer these enormous channel widths if the best practice is that we don't use them?
Yeah, it's actually, that's a good reminder. I was going to bring up some data sheets. I'll do that in a second. It depends on the vendor, and it depends on what their angle is with marketing. So some of the wireless LAN vendors are getting more smart about users themselves, or even engineers being smart, and they're not trying to overhype or overmarket it. But as you sort of head to more your consumer grade or small to medium business, when you're getting less educated people trying to make the purchasing decisions, all they see is the numbers, and the bigger the number, the faster the number, the better. And that's purely what it comes down to. I mean, even if you're looking for a brand new car, if you were comparing kilowatts or horsepower versus another car, you're going to look for a higher number, aren't you? It comes down to simple numbers, and that's really what the marketing teams are aiming for. So let me just bring up, let me just swap my screen around. Let me just bring up a data sheet here. So I'm going to bring up a data sheet for the Aruba AP315 that I had in the demo before. So in this spec sheet here, it says it can do 5 gigahertz 802.11 AC 4x4 MIMO, max rate 1733 megabits per second. So that's pretty cool. What I want to do is bring over that MCS table and try and scale it properly on the screen that you can hopefully see it. You can sort of work 2 ways on this. If you know what your MCS rate or spatial streams are and your signal to noise ratio, you can look at your data rate, or you could look at an advertised data rate such as 1.733 gigabits per second and work backwards this way. So in this particular example, for what Aruba have quoted, 1733 fits right here on this table, and this is with 160 megahertz wide channels, which is a bit unrealistic in today's environments, short guard interval, which is certainly achievable, and MCS Index 9, which means you've got to have the highest quality signal to noise ratio, at least 31 dB, and using this coding and modulation scheme of 256 QAM. So Jerry and Nick, you guys probably know that that's hard to achieve unless you're right near the access point and there's no background noise, and you've got to have 2 spatial streams. So what I like about the Aruba spec here is that they have specified a more realistic number for a more realistic device. They haven't just quoted a 4x4x4 spatial stream capability, given that there is none of those devices. So that's quite cool. But I also wanted to highlight further down, you can get into a bit more detail. They talk about, let me just clear those annotations off. They cover a few more specs around here with, VHT and single user MIMO, but further down you get into the actual radio specs of supported data rates. And what I want to highlight here is, while they've given that 1.7 megabits per second, 1.7 gigabits per second earlier, you have to make a note of, they've said you can do NSS is number of spatial streams. So you can do 1 to 4 spatial streams only with 20, 40, or 80 megahertz wide channels. You can only achieve 2 spatial streams on the AP side of things with 160 megahertz wide channels. So what that means is it correlates back to that what they put in their data sheet. They weren't just being nice in terms of device capabilities. They're basically saying that our access point can only do, let's bring it back up again, our access point can only do 2 spatial streams to get that maximum throughput. So I really like that. That's really honest of Aruba. That's some cool figures there. Let's just do a comparison of Cisco 4800, which is released recently. They've broken theirs down into Wave 1 and AC Wave 2 capabilities, which is quite nice. They've specified, 4x4x4, multi-user MIMO, 3 spatial streams, and you can see a comparison between Wave 1 and Wave 2, both 3 spatial streams, but they've got 20 to 80 megahertz wide channels up to 1.3 gig with 80 megahertz and 5 gigahertz. That's quite nice detail. Here, with 160 megahertz wide channels, they've set up to 5.2 gigabits per second. That is pure marketing speak. So that's where we come back to this MCS Index table. 5.2 is not even on here because we don't have a 4 spatial stream client. So even if we looked at the maximum that we have 3x3x3 spatial streams and looked at this 2.3 gigabits per second, that's very unlikely that you're going to get that these days. Whereas the 1.3 gigabits per second they mentioned before with 80 megahertz wide channels, what they're referring to is this number down here. So we've got 80 megahertz wide channels, short guard interval, MCS 9, and this coding and modulation scheme with the perfect SNR is where you would get 1.3 gigabits per second theoretical associated rate, not your real world throughput. So that's just an example of how you can break down those numbers.
Hey, Stephen, on that spec sheet, where are they getting the 5.2 gigabits?
So let me just bring that up. It's defined in the standard, right? So let me just bring up another screen. I'll try and find it. There's a table on Wikipedia which refers to it. Let me just make sure I can find it.
Is that on a single band or is that both bands combined?
So that's based on, I think they're talking about the dual 5 gig mode, and they're talking about doing 4 spatial streams, and they're talking about 5.2 gigabits per second on one radio, not one device. Let me just see.
Okay, so they are talking about one radio, just not necessarily talking to a single device.
Yeah. So let me just bring this up. It's not quite specific to the 5.2 gigabits per second. Let me just clear that annotation off. This was a bit of consumer grade router marketing where they said that they could get up to these sorts of speeds because they had 2 separate 5 gigahertz radios that could do 2.2 gigabits per second each. So they were saying on their marketing spec, oh, we can do 4.4 gigabits per second concurrently. But that's not what an actual device could use. It was just what the radio was capable of. So that's where the Cisco AP saying it can do up to 5.2 gigabits per second. Sure, if you have an 8 spatial stream 8 spatial stream client, which is what the 802.11ac standard can say you can have by maximum, but you're never going to see one of those in the marketplace before 802.11ax comes out.
Okay.
Right,
okay.
Steve,
So yeah, there's.
Sorry, Jerry, you go.
Sorry about that.
No, it's all good, man. It's all good. You go for it. No,
so
I wasn't.
Cool.
So I was just going to say, this is all on the AP side, right? How do we find out the specs of the clients and know what the client's capabilities are?
Yeah, that's a good question, Jerry. There's a couple of ways you can do it from a slightly technical point of view or a very technical point of view. If you look at Apple iPhone specs, they will tell you that they're 802.11ac capable, and they will tell you what channel bandwidths they can support, but they don't generally say what data rates they can support. So you could probably go into the FCC website to have a look at the different reports and tests they've done on there, where you can find out capabilities such as spatial streams and channel bandwidths and maximum and minimum transmit powers. Or if you're more technically minded and you've got the capability to do packet captures, whether you're doing packet captures with a Windows PC or a Mac, or even doing some packet sniffing from an access point, or using something like a wireless LAN Pi, you can technically you can go into the beacons of a probe request from a client device and see what its capabilities are there. It'll tell you the number of spatial streams it supports. It tells you the channels that it supports from a country regulation standpoint, and it'll tell you what bandwidth it will support and what data rates. So it'll actually give you a table of what MCS indices and rates that it can support. And even some of the wireless LAN network monitoring dashboards these days, such as Meraki, Mist, Cisco, because those access points are receiving those beacons all the time, they're feeding that information into their network management dashboards, and they'll actually give you a view of what the capabilities are of those devices, which is pretty cool. So that's becoming more and more common from the wireless LAN management point of view.
Yeah, and I was going to plug the clients.mikealbano.com website as well. I feel like that's relevant to this conversation. It's a good database that's exactly what Steven's talking about, where wireless engineers have captured those frames. So the clients will advertise their capabilities when they connect to the AP, so the AP knows how to talk to the clients, right?
Yep.
So we can sniff that traffic and we can grab that information out of the air when a client associates to an access point, and we can use that information. That's exactly what Mike has done here, is built a database of all those frames of these clients advertising what their capabilities are. And if you kind of scroll over to the right of that database, you'll see there's a number of spatial streams. There's an SS column, which is for spatial streams, and even the maximum transmit power that the clients are advertising to the AP. And this is all on the 5 gigahertz side, but that's typically what we're designing for anyways. So that can be a really useful website to leverage.
Yeah, that's great. Thanks for bringing that up, Jerry. Yeah, it is a fantastic website. So, and that's actually crowdsourced information too. So if you ever do a packet capture of an association request or a probe request, you typically can get that information and submit it to Mike's website and see what's in there. But
Yeah.
it's got most of the latest and greatest devices in there. So yeah, thanks for bringing that up, Jerry.
Yeah, it's a good point. It is all crowdsourced. So if you do see that you've got a device that isn't on the list, I would definitely encourage you to click on the how to contribute and contribute. He walks you through all the steps of doing those captures and sending that in. So if you're up for the challenge there, I've submitted a few in there, and Mike's really good about getting those updated on the database pretty quickly.
Awesome. Actually, to that point, in terms of client capabilities, when we're designing client capabilities in Ekahau, we have a few built-in capabilities, such as generic smartphones and laptops and tablets. But Ekahau also has the capability to customize those and suit those to these devices that you're deploying on your network. So you can use this information from clients.mikealbano.com, or you can use information from the FCC website or any other means, and then input that into Ekahau Site Server to help with your capacity planning.
Do we have time for a couple more questions?
Yeah, I think we've got another 10 minutes or so for some more questions.
Super. So we've got one here from Mohammed Fikri. So just asking, what is the best way to check the throughput of our wireless network?
Good question, and that brings us back to where I was showing the difference between the data rate versus throughput visualizations in Ekahau. So you can do an active throughput survey in Ekahau using an iPerf server set up on your local LAN. That could be a Windows or Linux iPerf server, a Mac, doesn't matter what it is. You could use a wireless LAN Pi, a few other devices, but we also have an ePerf version of iPerf, which is more friendly to roaming events. Jerry might be able to go into a bit more detail on that in a minute, but basically you can set up an active survey as part of your walk-around survey on a site. So you're collecting all of your Wi-Fi and RF through the Sidekick, but then also associated with your laptop or tablet NIC, you can do constant throughput tests as you're walking through your environment. Some people will use continuous surveys as they're constantly walking throughout a facility or a site to collect that data. Some people choose to do specific stop-and-go surveys in particular locations, particular rooms, or maybe meeting rooms that are going to be higher density, and doing specific throughput tests in that room as well. And you can use that to complement your user acceptance testing when you're doing a Wi-Fi deployment.
And just one thing, Go on, Jerry.
No worries, Nick. You go.
I was just going to say, just to be clear here, like if you're doing a throughput survey with Ekahau, what is managing that association? Like, which piece of hardware is actually associated to the network, and who's managing that association?
Sure. Let's do that with a little bit of half of a demo, because I don't have an IP throughput server running at this point in time. On macOS, the only control you have over a active survey, whether it's ping or throughput, is via your built-in internal Wi-Fi NIC, and you'll see that here in the options here for survey settings. And you can set this to either ping. Oops, let me just clear that. Ping or throughput. So that's using your inbuilt Mac Wi-Fi NIC associated to an SSID. If you're on Windows, you could do the same with your internal NIC, but Windows, you can also use external USB NICs if you wanted to. I know some big deployments where field engineers might have had all sorts of different laptops or tablets that they're surveying with, but to standardize the throughput or ping tests, they've had, the exact same model of ASUS USB Wi-Fi NIC connected to that laptop while they're doing a Sidekick survey, purely just to standardize the device capabilities for those tests that they're doing with either throughput or ping surveys.
Okay, but so it's your operating system that's managing this association, and we choose what hardware to use when doing a throughput.
That's correct. Yeah, that's correct. And it's completely separate to the Sidekick. The Sidekick's a passive survey device. The Wi-Fi radios and that are just listening to beacons that are being advertised, and the spectrum analyzer is just receiving all the spectrum signals in.
Fantastic. Jerry, I cut you off earlier. What were you going to say?
Oh, I was just going to do my shameless plug for my little side project, the wlandpi.com. I put a link to it in chat there, but yeah, that was a kind of a very tiny little device with a gigabit Ethernet port on there that we built for the Wireless LAN Pros conference here in the U.S. Back in February, and yeah, that's exactly the kind of the purpose. So if you're Mohammed, if the question was around, what's the best way to check the throughput on the wireless network around the server, the endpoint piece of it running some type of iPerf instance, that's exactly what this kind of little piece of hardware was meant for. So this is a very portable throughput testing endpoint that you can plug into any point of the network, and then using the Ekahau Site Survey software, you can point the your host device, that being the host device, and point it to that and measure that throughput. So kind of think of it as a reflector, right? So you're sending out packets, over the wireless, over the wired to this throughput device, and then it's replying back telling you what your actual throughput performance is, and you can measure in either direction, either sending or receiving through the network.
Great. Any other questions, guys?
Yeah, we got one more question here. If you've got any more questions, go ahead and get those submitted here quickly. We got a few minutes left, but we'll go ahead and answer this one from Michael. What are some common sources of 5 gigahertz interference that you've come across?
Great question. And I like where that's leading.
What was that?
I said I like that question, and I like where it is leading.
Exactly. That's what I was thinking. Do we have the ability to do maybe a live Sidekick demo? Do we have any even maybe sample interferers? I do have a project file I can pull up with some 5 gigahertz interferers otherwise.
Yeah. I've got my Sidekick running here in the background. Let's swap this over to 5 gigahertz. My 5 gigahertz is nice and clean where I am right at the moment, which is perfect for this demo. So those that aren't familiar to the Sidekick, what we're seeing here is right in the middle, we've got the live spectrum view of 5 gigahertz frequency. Over on the right, we've got the radios that are visible to the Sidekick that we're receiving beacons from. On the left-hand side, we've got some waterfalls and historical views of spectrum and signals there. 2.4 looked a bit more interesting because it's a bit more crowded. There's Bluetooth and stuff hopping around there from my mouse and my headset there. But because the question's focused on 5 gigahertz, I'm actually going to give you guys a sneak peek at a new feature coming out in ESS 9.2, which is interferer detection. let me fire up this camera here, and I'm going to make this full screen so you get a better view. What I've just fired up here is a little drone camera. So it's non-Wi-Fi. I'm just going to clear this for a minute because it gives you a better view of it. This is a non-Wi-Fi interferer, and it's just covering channel 108 there pretty intensely. Let's just zoom in a bit more. I'm going to move my control panel out of the way. Give you a better view of it there. So it's quite a strong dark signature. So as you go from green to yellow to orange to red, blue to black, the black is representing a very highly utilized channel. And we can actually change this view down the bottom to have a look at channels and have a look at the channel 108 down here where we've got 50% utilization on that channel, which is pretty much going to kill any Wi-Fi activity on that channel. So what I had before is the interferer detection. Let me just turn that back on, and it's come up as a video transmitter. So we're basically enabling it, making it easier for troubleshooting with the Sidekick while you're out in the field. So you can go, okay, I've got something weird here happening, which is kicking my Wi-Fi clients off the channel. Maybe my access point or wireless controller can't tell me exactly what it is, but you know, we can see right here it's a video transmitter, or maybe you might have a 2.4 or 5 gigahertz motion detector. 5 gigahertz motion detectors is what I see quite commonly, definitely in warehouse surveys where they'll pop up. Other 5 gigahertz interference, whether you call Wi-Fi interfering on radar or radar interfering on Wi-Fi, that definitely impacts Wi-Fi on your Uni 2 and 2E bands. What other interferers have you guys seen?
Yeah, well, the first one that comes to mind anytime you're talking about 5 gigahertz is going to be DFS, right? So DFS events, I should say. So on you know, the 5 gigahertz bands, we've got some extra considerations that we don't have on 2.4, and DFS is one of those. So DFS stands for dynamic frequency selection, and that DFS events can be triggered by things like weather radar. So anytime that signature or that pattern is heard, these access points, if they're occupying those channels and those DFS spaces, the APs have to move off of those channels, right? They have to change channels quickly. So that can be an issue where, you know, clients could be getting dropped in the process of you know, they'll advertise that they're moving off the channel, but then immediately they abandon the channel and go to a non-DFS channel typically, depending on the vendor. So yeah, that can be a different type of interference, but interference nonetheless.
That's right, and every vendor deals with that event differently. Some APs and controllers will tell you specifically why it's changed channel due to a DFS event, or even what channel and which AP is impacted. But other vendors, depending on the way that they've designed their hardware or implemented it, some of them can be extremely sensitive, and maybe a 5 gigahertz motion detector can actually fool the AP into thinking it's a DFS event. So you can have different impacts on your Wi-Fi due to those interfering devices.
We've got
Aaron. Oh yeah.
Oh yeah, Nick.
No, Aaron's chipping in to just share with us that. So yeah, wireless sensors that turn on lights often operate in the 5 gigahertz range, and we can. I can confirm that because off of eBay, I bought a motion detector that operates in the 5 gigahertz band, and it pumps out a very narrow, very loud spike of 5 gigahertz energy.
Yeah, that's what I was meaning by 5 gigahertz motion detectors. Whether they're used for security or whether it's for turning lights on and off, I've definitely seen that. I've seen it in warehouses where it's used for security zoning, and also to automatically zoom CCTV cameras into people's locations. I've seen 5 gigahertz motion detectors for that, causing spikes. And like you said, Nick, they're really, really short, sharp, powerful spikes. So think of this video transmitter, but shorter, but equally as dense in terms of highly utilizing that channel. And it's enough to drop the beacons from the point of view of a wireless device and effectively render that channel, inaudible.
Well, I see we've got, we're right at the top of the hour here, but we had one more good question come in. So if you guys are all right, let's see if we can get this one answered.
Sure.
Mario asked, what would be the ideal deployment where 80 megahertz or 160 megahertz can be used. And if you guys are familiar with GT Hill in the industry, he comes to mind when that question is asked, because he literally owns a bunker underground. And that's what I think of anytime somebody asks about where I should use 160 megahertz. But realistically, where would we use 160 megahertz channels in the real world, or even 80, right? What do you guys think?
I would only use 160 megahertz channels if you only needed one AP and you were the only person for a couple of 100 meters in your surrounding environment, and you had no other Wi-Fi or that could bleed into your environment, and you have devices that are capable of 160 megahertz, then you could use, or safely use, a 160 megahertz wide channel without any overlap or reduction in throughput in your environment. If that's what it was, like is shown on the screen at the moment, with only one AP, no overlap coming in from exterior sources, and devices that could support up to that channel bandwidth. I'm not actually sure of any devices that can do 160 megahertz, just like for spatial streams. So that would be one consideration. 80 megahertz wide channels would be the same sort of thing to another degree. You can have multiple APs because you have more non-overlapping channels. You end up with 1, 2, 3, 4 in Australia, for example, but still that's only 4 non-overlapping 80 megahertz wide channels that you could use. Again, if it wasn't a high density AP deployment and you didn't have any interfering Wi-Fi from neighbors around you, then you get some benefit out of using 80 megahertz wide channels.
Yeah, and I would add to that the rule of thumb that I've really learned, actually I think this came from Keith Parsons, is use the widest channel possible while avoiding co-channel interference. So as soon as you start to introduce co-channel interference, you need to back off on the channel width. So if you can deploy your entire wireless deployment with 80 megahertz wide channels and not introduce any co-channel interference, then use 80 megahertz wide channels. There's no reason why you shouldn't, for the most part. But the problem is you're almost always going to introduce co-channel interference in any type of enterprise deployment where you have multiple access points, and any type of high density deployment where you have lots of radios to support the users.
Let's just quickly show that on the webinar here. We're deploying multiple APs. Yes, they're all on channel 36 at the moment, but we'll change that. Let's change them all to 80 megahertz channels. And that's not too bad. We're not getting too much channel overlap there, but that wouldn't be a typical representation of a high density deployment these days. If I added in one more in there, that's really going to upset things, and you're going to start to have more than one overlapping channel. So it's kind of hard to avoid if you're trying to get real high density, especially if you're using some of the latest APs these days that can use dual 5 gigahertz. There's no way that you could have 80 megahertz channels on both radios on each access point. You'd be just interfering with your own radios then.
Very good. Nicely done, Stephen. Well, I just want to thank everybody for joining today's webinar. Hopefully you guys found this to be insightful and useful information for you. If you do have any other questions that we didn't get a chance to answer, please contact myself, Stephen, or Nick. You'll also receive a follow-up email within 24 to 48 hours with a link to view the recording of today's webinar. But yeah, on behalf of Ekahau, just want to thank you everybody for joining, and have a great rest of your day.
And thank you, Jerry, and thank you, Nick, for joining us.
My pleasure. Thank you, everyone, for joining.
Thank you. Bye-bye.